So to summarize this chapter, we have to remember the most important thing, that is the near perfect analogy between diffusive mass and heat transfer. Now we did single layer for a slab. For a cylindrical or a spherical shell, we use the same resistance approach as we used in heat transfer. The resistances are simply rewritten, replacing thermal conductivity by mass diffusivity. Likewise, for concentration profiles, the same equations as we derived for a cylinder, for example, in heat transfer, can be used here, and the same for sphere. Then we did multiple layers. So for multiple layers, we did a slab. We did a slab with two other resistances. As for single layers, the multiple layers can also be extended to other geometries by simply using the resistances in those geometries. We then did presence of reaction. So all these others were with no reaction. Now it's presence of reaction in single layer for a slab. We did this for a first order reaction, and actually it's first order elimination, so it's a negative term for the generation. We could do one for the positive. We did not do for zeroth order reaction. This is much easier, and we can follow the same process as we did for the first order reaction. Now, when reaction is present, analytical solutions for these other two geometries get harder unless it's zeroth order reaction. Zeroth order reaction for slab and cylinder, we can readily start from governing equation, boundary conditions, and get our concentration profile and flux. Another way to summarize for problem solving this chapter on steady state diffusion is as follows. Given a problem at steady state, we check whether it's with reaction or without reaction. This is exact analogy to steady state heat conduction with heat generation or without heat generation. When there is no reaction present, that's here, resistance formulations are often sufficient. This is particularly true for multiple layer problems. If somehow resistance formulation is not available, if this is not available, then we can always get derive things from scratch by solving the governing equation and boundary condition for single layers. With reaction, that's here, if the condition matches with what we did, that is slab with first order reaction, and that too a reaction that is a first order elimination, so it's a negative generation term. If that is what we're talking about, we can simply use the solution in the text. For any other situation, for example, if the reaction changes to zeroth order, or there are changes in boundary condition, then we have to derive from scratch by solving the governing equation with the boundary conditions. When we need to start from scratch, here is a step-by-step solution procedure that might be helpful. So we start from a physical situation, and then we get to a schematic, and then we get to the governing equation, then we get to the boundary condition, and then we solve. Now, little more details of this process. When it's schematic, when doing the schematic, the most important thing perhaps, uh, based on the types of problem that we are doing here, is what is my region? What region are we solving? Am I in the solid or in the fluid? So what is my domain? And then next, useful thing would be to see if there is symmetry condition that is satisfied. That helps us to set, for example, boundary condition. Then for governing equation, there's number of things to consider. First, what geometry most closely approximates the situation, Cartesian, cylindrical, or spherical? Then is it going to be a 1D, 2D, or 3D problem? Everything we did has been 1D. Then after that, we have, for the 1D, when we have the equation, the governing equation, it has four terms. Okay, so what are those four terms? A transient term, then the term due to flow, if there's a velocity, then diffusion, and this is not storage, but it's reaction. So reaction term. Okay, so those are the four terms: 1, 2, 3, 4. And the most important thing now is to see which terms do I need to keep. As we keep the terms, of course, the solution process gets harder. Finally, for boundary conditions, we have to first decide how many boundary conditions, so that when we have a second order term like del square t del x square, and in this case, in this chapter, del square, when we have a second order term, then we need two boundary conditions for that. Then we need an initial condition for time, that's here, for transient processes. Then we decide what type of boundary condition is it. This is often a bit harder. Is it concentration given? Is it flux given? Or is it convection? So once we have all those, now we have defined the governing equation and boundary condition, and then we just get into the detailed solution.